Chapter 3 is machine learning workflows. And the goal here is simply to kind of lay out some classic machine learning workflows for you as you do your projects. This is going to be a classical machine learning approach. So this varies very different from a deep learning approach where you might feed raw data into a neural network. In a kind of classical machine learning approach, you're always going to have to develop features. And so you might have kind of 6 steps, right? There's kind of 6 commonly accepted steps to a machine learning workflow. And first is the most fun, and that's just collect your data, right? And then you want to inspect and clean your data. So that's why it's always important to do some data visualization, maybe do some unstructured machine learning when you first get your data. You just want to be knowledgeable about what's in your data. And then you might engineer some features, right? So on the Ames housing data set, that's pretty easy. Number of bathrooms, number of bedrooms, square footage, right? But maybe a good feature is actually something like the ratio of bedrooms to bathrooms, right? Do you want a house with 9 bathrooms and 1 bedroom? Probably not. Or 9 bedrooms and 1 bathroom? Probably not. So maybe a ratio, right? And that might be an engineered feature as opposed to like a counting feature. And then you do what everyone thinks is important, right? Which is just train your model. And that's the fun part. And then we have the testing the model stage, right? So that's splitting your data up. And then we have kind of the improve your model stage, which is where it circles back. And so the problem there is that if you can overtrain if you go back and forth too much, but it's definitely pretty much always going to be iterative. And the goal is to keep some data on the side to help prevent those overtraining issues. Now, when you are developing engineered features, there's a couple different ways you can do this, right? So I made this little flow chart and wrote out some features that you can use. And these are very prevalent in kind of engineering systems where a lot of your data is time series based. So we have raw data, and then I go into feature engineering. That's going to be very important. And maybe I have statistical features. This figure is wrong. I have time series features, and then I have frequency features, right? And so we'll give you a list of features that you can use, and the idea here is that you might have time series data from a sensor that's measuring voltage, or maybe something that's measuring angle, or something that's measuring weight, something along those lines. And you can go ahead and extract features from that information, and then you can figure out which one of those features might be more robust or meaningful or has more information. And these are kind of above and beyond, just your typical like integer-based counting features. So if you look in the text that's provided, there's equations for all of these, but it's just too many equations to put on a slide. And so we'll start with statistical features. These are your fun ones, right? Max, min, mean, absolute mean value, RMS, root mean square value. So those are the ones that we all know pretty well, right? You could have a voltage signal that's coming in. You take your absolute average of your signal, your min, and your max, and that's 3 features, even though your voltage signal may be 40,000 points long, right? You can also look at some more complicated ones, right? If you consider standard deviation complicated, but it's kind of the end of the simple ones. And then you can have second order skewness, kurtosis, shape factor, crest, and impulse. And that can help you find things like your peaks and effective magnitude, largest peak relative to your effective level, kind of largest peak relative to your average magnitude. These are really helpful and kind of instantaneous type responses that might be happening in your signals. This is just kind of a list of good statistical features that you can pull from. Now with AI, you can just ask AI to create a quick function for you and run your data through all of these. Time series features are much more interesting, right? So if you have some data, it's time invariant. Other data is not time invariant, right? It depends on the data point that was before and after it. And so you might have like a lagged value, your first difference, your rate of change, your moving average, your rolling standard deviation, your rolling max, your rolling min, or your zero crossing rate, right? That's how often it goes from positive to negative or negative to positive. These are all time series features. So as you're developing your projects and you're looking for features to apply, you can pick out some of these. Probably my favorite is going to be the next one, which are your frequency domain features, because these take a little bit of conceptual capability to track around. They are time-based in the sense that you're trying to look for repeating patterns, right? A lot of times in your data, you might not care about the min or the max. You just want to know what's going to repeat. So you can always do your dominant frequency, right? So that's what's the repeating pattern with the most energy in your signal. Your spectral centroid and your bandwidth, where does that signal center about, and how wide might that signal be centering about that if you have leakage. And then a couple that I really like, I've got a low frequency energy ratio, a mid frequency energy ratio, and a high frequency energy ratio. If I split my frequency components that I'm looking into three, do I have most of my energy in my mid, my medium, and my high? One thing to think about that is if you have a lot of data points, you can actually get, your FFT will give you out, if you have 10,000 data points, sampled it, your Nyquist frequency is half of that, right? So 5,000. And so you might be, you have a high frequency component to it. But you're typically going to be interested in probably like the first 5 or 10% of your frequency component, and then you would split that into low, medium, high. Don't just take the frequency, like the entire frequency component, because all of your information is going to be in the low amount. So you can move this up and down, but then you can get your frequency ratios. And then you have your high to low frequency energy ratio and a peak to total energy spectral ratio. I find it sometimes very valuable when you're running features, just to run through a lot of features, even if you end up not using them, right? It's good to test 30 features, 20 features, and then just pick the top 5. And like when you're writing papers or writing reports, it's always good to say, hey, I started with, a traditional 30 from this random book on machine learning from the University of South Carolina, and then I down selected to the top 5 that were of interest. And kind of helps show that you had some diligence in setting those up.